When we look at the solar system from the outside, it looks like a well-oiled machine. However, between the orbits of Mars and Jupiter is a veritable sphere of chaos. In it, hundreds of thousands of small celestial bodies move through space in different directions, sometimes crossing the orbits of others. Sometimes they collide and form thousands of parts. Its face is constantly changing, and it is impossible to predict what will happen in the distant future. We're talking, of course, about the main asteroid belt, one of the most unstable and mysterious regions of the solar system. Currently, more than 300,000 small celestial bodies in this sector have been named or given numerical names. At the same time, their total number can exceed 1 million. The beginning of the study of the asteroid belt can be considered 1801, when astronomers, after a long and persistent search, discovered a mysterious object in the sky. Its parameters corresponded to the planet, but it was so small that its disk could not be seen even by the best telescopes of the time. The discovery appeared in the eyes of scientists as a bright point, similar to a star. The celestial object was named Ceres, and soon other objects of this type were discovered. A new term had to be coined for them. Unusual celestial bodies were called asteroids, which literally means star-like. In addition to asteroids, this region of the solar system is full of large amounts of cosmic dust. Tiny particles, moving slowly in a spiral, scatter the sun's rays, creating a very faint, dim glow. This radiation is called the light of the zodiac, and in the equatorial regions of the Earth, it can be seen even with the naked eye. For a long time, there was a generally accepted hypothesis in society that the objects in the asteroid belt represent the remains of a destroyed planet. However, this assumption is currently considered unacceptable. First, the combined mass of all the main belt objects is very small, totaling only 3 by 10 to the 21st degree kilograms, or 4% of the Moon's mass. Even if we assume that a significant part of the asteroids have long left the belt, the total mass of rocky debris is not enough to form an object close in size to a full-fledged planet. Secondly, calculations show that the formation of large celestial bodies in this sector of the solar system is hindered by the gravitational influence of Jupiter. According to the results of mathematical modeling, the largest formations in the belt never exceeded 1,000 kilometers in diameter. The impact of the giant neighbor made their orbits unstable, causing potential protoplanets to collide with each other, collapsing into smaller fragments. Traces of these catastrophes can still be seen. Most of the most important objects of the belt are united in the so-called families, groups of asteroids similar in composition and origin. They were probably formed as a result of similar destructive collisions. The main zone has no clear boundaries. Most of its constituent objects lie between 2.06 and 3.27 AU. These boundaries were created by Jupiter's tidal influence and are called Kirkwood rifts. All celestial bodies falling into these zones experience a powerful gravitational pull of a massive gas giant, changing their orbits. Therefore, the density of space objects in these regions is much lower than outside them. Kirkwood fractures occur not only at the conventional boundaries of the zone, but also within it. The two most obvious ones are located at distances of 2.5 and 2.82 AU from the Sun. It is also conditionally possible to divide the asteroid belt into two large parts, inner and outer. The boundary between them is considered the Kirkwood gap, with a radius of 2.5 AU, which corresponds to the strongest resonance in the orbit of Jupiter. Beyond the Sun's belt is Ceres, the largest object in this segment of the solar system. For some time it was considered a planet, then an asteroid. But finally in 2006, the celestial body received the status of a dwarf planet. This is possible because, unlike most other objects in the belt, Ceres is round. It has a diameter of about 940 kilometers and a mass of about 4 by 10 kilograms to 20th stellar magnitude, which is about a third of the total mass of the asteroid belt. Thus, Ceres is about 6,000 times lighter than our planet. The dwarf planet is at the farthest point of its orbit, at a distance of 2.9 AU from the Sun. At perihelion, the distance from SRR to the center of the system is about 2.5 AU. Currently, its surface temperature can rise to 239 Kelvin or minus 33 degrees Celsius. However, the planetoid's average temperature is significantly lower at only 167 Kelvin or minus 106 degrees Celsius. The celestial body is believed to be formed from a rocky core about 100 kilometers thick, surrounded by cryomantle. Water ice thus occupies up to half the volume of the dwarf planet, or 20 to 30% of its mass. In the inner part of the belt is Vesta, the largest and most massive known asteroid in the solar system. The average diameter of the object is about 525 kilometers, and the mass is about 2.6 x 10 kilograms to the 20th degree. That is almost 4 times smaller than the CDR. The orbit is quite elongated. Ophelia is 2.57 AU, and perihelion is about 2.15 AU. In this case, the celestial body makes a complete revolution around the Sun in 3.6 Earth years. It is also noteworthy that Vesta is the only asteroid that can be observed with the naked eye. This is possible not only because of its large size, but also because of its relatively light surface, which reflects about 42% of the light falling on it. In addition, the minimum distance between Vesta and the Earth is small and is only 177 million kilometers or 1.18 AU. We assume that the internal structure of Vesta is similar to that of a full-sized planet. It appears to have a metallic core of nickel and iron and a rocky mantle. Currently, the temperature on the surface of the asteroid ranges from minus 190 to minus 20 degrees Celsius. However, the asteroid has been significantly warmer in the past. The dark areas on the surface in the Western Hemisphere are most likely basaltic plateaus. Such landforms could be formed by volcanic activity or by collisions with massive cosmic bodies. The most remarkable detail of the asteroid's topography is the giant impact crater Rhea Silvia, which has a diameter of up to 500 kilometers and a depth of about 25,000 meters. In its center is the second largest mountain in the solar system, the height of which exceeds 22 kilometers. It is not difficult to see that the diameter of the crater is comparable to the size of the celestial body itself. Apparently, the asteroid had collided with a really large object earlier. As a result, Silvia Ray did not form a crater, but many small fragments, which are now classified as part of the large Vesta family of asteroids. It contains more than 15,000 objects, which is about 5% of all known large objects in the belt. It is believed that most asteroid families were formed as a result of a catastrophic collision between two large celestial bodies. Sometimes gravity pulls the resulting debris together and forms a new astronomical object. However, it no longer has a monolithic structure, and astronomers sometimes informally call such formations garbage masks. Such celestial bodies probably include, for example, Silvia, one of the largest objects in the asteroid belt. Its dimensions are approximately 384 x 262 x 232 kilometers, and its mass is 1.5 x 10 kilograms to the 19th degree. Thus, the average density of an asteroid exceeds that of water by only 20%. Calculations show that cavities can make up 25 to 60% of its volume. Silvia makes a full revolution around the Sun in 6.5 years. At the farthest point of its orbit, the distance from the object to the center of the system is 3.7 AU. Perihelion reduces the distance of the celestial body to 3.2 AU. The perihelion reduces the distance of the celestial body to 3.2 AU. Some debris from the collision is not expected to attract other debris, but to become satellites of the new celestial body. Silvia has two known satellites, Romulus with a diameter of 18 kilometers and Remus with a diameter of about 7 kilometers. Their design is not yet fully understood, and it is likely that these objects are not monolithic. It is also possible that Silvia has smaller satellites that have not yet been discovered. Another notable object in the asteroid belt is Pallada. It was discovered in 1802, just after Ceres, and is the second largest asteroid in the zone. The celestial body has an average diameter of about 512 kilometers and a mass of about 2 by 10 kilograms to 20th stellar magnitude, which is about 25% smaller than Vesta. The asteroid's orbit is highly elongated and inclined by 35 degrees with respect to the ecliptic plane. Therefore, this celestial body is considered difficult for Mars rovers to reach. Pallada makes a complete revolution around the Sun in about 4.6 years. In addition, the distance from it to the center of the system varies by more than a factor of 1.5, from 2.1 AU at perihelion to 3.4 AU at aphelion. Pallada's surface is covered with many craters, rougher than on the larger Ceres or Vesta. Studies of the asteroid's surface composition show that it consists mainly of siliceous rocks with low iron and water content. Like Vesta, this celestial body is expected to be one of the few remaining possible protoplanets. This means that studying it can provide important information about the formation of the solar system. Unlike Vesta, most asteroids cannot be seen with the naked eye, even with amateur equipment. These include Interamnia, one of the most enigmatic objects in the core zone. It is an irregularly shaped asteroid with dimensions of 362 x 348 x 310 kilometers and a mass of about 1.2% of the total mass of all objects in the zone. However, despite its relatively large size, Interamnia is still a very understudied body. The reason is that the surface of the asteroid is very dark and absorbs about 93% of the light falling on it. Interamnia belongs to the extremely rare spectral class F, a subclass of carbonaceous asteroids. Studies of its brightness show that the surface of the celestial body is remarkably uniform in color, which means that it has not experienced strong collisions for a long time. The density of the asteroid is not very high. It is only twice as dense as water. It is believed to be composed of a hard rock core surrounded by a thick layer of ice. In addition, the surface of the object is covered with a large amount of fine and dark dust. Interamnia makes a complete revolution around the Sun in about 5 years and 4 months. Its aphel is located in the opposite direction to the 4 largest objects in the main belt. Its distance from the Sun ranges from 2.5 to 3.5 astronomical units. Theoretically, the asteroid's orbit crosses the orbits of large objects, such as Ceres and Pallada. But calculations show that a collision is highly unlikely. The main belt contains millions of objects, from dwarf planets to small meteorites the size of cobblestones. However, the distances between them are several thousand and even millions of kilometers. Therefore, the probability of an accidental belt spacecraft approaching a celestial body is extremely low. Mathematical modeling, however, shows that observed collisions in this region of the solar system occur about once every 10 million years, becoming the source of a large amount of new debris. Although a manned mission to the main belt asteroids is still a long way off, some of them have already been studied by interplanetary space probes. For example, the Dawn probe studied Ceres and Vesta between 2011 and 2016. And recently, the Lucy research umbrella left Earth. Although its primary target is Jupiter's Trojan asteroids, the spacecraft will approach and photograph a main belt object named Donald Johanson in 2025. Meanwhile, Project Psyche is scheduled to launch in July 2022, targeting the largest known metallic asteroid in the main belt. The mission plan calls for the probe to reach its destination in early 2026 and then spend at least 21 months orbiting the asteroid, studying the topography, composition, and magnetic field of the celestial body. Despite their small size, asteroids are important both scientifically and practically. Some of the zone's most important objects are true treasures, preserved from the very beginning of the solar system. Their research is likely to help us better understand the formation of planets and other celestial bodies. And in the future, asteroids are likely to be a source of resources for space exploration. How soon that time will come is not yet known, but each new rocket launch brings the space age closer. On the outskirts of the solar system, in the middle of the cosmic abyss, a small world, bound by poisonous glaciers, is hidden. A giant shadow hangs motionless over the barren horizon, obscuring the stars, and a dark sun slowly creeps across the black sky. Its rays cannot dispel the darkness that for centuries has enveloped a frozen plain cut by a multitude of bottomless cracks. This is Pluto, a lifeless realm of stone and ice, hidden in eternal shadow. Let's get to know it better. Pluto, located about 40 AU from the Sun, is a dark, hard-to-see object. This distant celestial body moves around the center of the solar system in a greatly elongated orbit, making a complete revolution in 248 Earth years. Thanks to many calculations, we know that Pluto has a radius of 1,188 kilometers. This means it is much smaller in size than all the planets in the solar system, as well as some of their satellites, including the Moon. At the same time, observations of the movement of the celestial body itself made it possible to calculate its mass very accurately. It turns out to be small. That's only 1.3 in 10, 22 kilometers or 18% of a month. It is easy to see that Pluto has many more characteristics similar to smaller celestial bodies like Eridus, Ceres, or Sedna. Because of this, it topped the list of dwarf planets in 2006. Pluto's long and elongated orbit is the reason for its long orbit. It wasn't until 1989 that the planetoid passed the perihelion of its orbit for the first time since its discovery and approached the Sun at a distance of 29.7 AE. This distance has steadily increased since then, reaching its maximum in 2113. Currently, the dwarf planet is located near aphelion, 49.3 AU from the center of our system. Thus, Pluto is a very distant and little-known space object. That is why it cannot be seen from Earth with the naked eye. And even in images obtained by the Hubble orbiting telescope, the dwarf planet looks like a blurry brown disk without any surface detail. Of course, in such conditions to fully study the celestial body is almost impossible. In 2006, the New Horizons automated orbiter was sent to Pluto to tackle the problem. It spent a long 9.5 years on its journey, providing us with detailed photos of Jupiter. It wasn't until 2015 that the probe finally reached its primary target. While flying past Pluto, the station made about 400 observations, collecting more than 6 gigabytes of data. And to transmit such a large set of data to Earth, it took more than a year. Unfortunately, the surface of the dwarf planet could not be fully photographed because of the special trajectory of the probe. The thing is, New Horizons didn't circle Pluto, but went around it to study other objects. Before we delve into the details of the celestial body's topography, we need to understand its internal structure. According to the currently accepted model, Pluto has a massive core about 1,700 kilometers in diameter at its center, made up of a mixture of various water ice and rocks. It is surrounded by a 300-kilometer ice sheet, the tectonic processes of which are perhaps poorly understood. On the other hand, the mantle is covered with crust, which is a mixture of crystallized gases such as nitrogen, methane, and carbon monoxide. Some hypotheses suggest that Pluto's core may generate enough heat to melt some of its icy mantle. In this case, deep beneath the surface of the planetoid must hide a very salty and alkaline ocean containing large amounts of dissolved ammonia. At the same time, the surface temperature of the dwarf planet is very low and does not exceed 60 Kelvin or minus 213 degrees Celsius. Our journey on Pluto begins with the most remarkable and studied detail of its topography, the burial region. This vast area is located in the equatorial zone of the planetoid and is schematically drawn in the shape of a heart. This similarity has led to the region's unofficial name, Pluto's heart. Its size is 2,300 kilometers, which means that the plateau occupies about a quarter of the entire surface of the celestial body. The surface of the burial ground is heterogeneous. Thus, at its western end is the flatter and brighter Sputnik Plateau, which is 1,492 kilometers in diameter. If you look at the uplands map, you will see that this area is a large lowland. It is covered with a thick layer of nitrogen ice and carbon monoxide and methane in solid form. These substances have a bright color, because of which some parts of the plain reflect up to 90% of the light falling on them. In addition, there are almost no craters, which means that this area is geologically recent. According to the main hypothesis, the satellite plateau was formed about 100 million years ago when Pluto collided with a large celestial body. The result was a huge impact crater filled with the rapidly freezing contents of the hypothetical dwarf planet's hypothetical inner ocean. This can be evidenced by the characteristic features of the relief of some plains. For example, there are many smooth surfaces 20, 30 kilometers long with hills and valleys piled between them. This structure resembles the convection cells observed in any fluid heated from below, which may be indirect support for the hypothesis of Pluto's hot interior. The tomb region is framed by relatively high ridges. Thus, the Hillary Mountains, located to the west of the Sputnik Plateau, reach a height of 3.5 kilometers. And in the southern part of the heart, the Tenzing Mountains rise to the sky. Some peaks exceed the average surface level of the dwarf planet by 6 kilometers, making this array the highest mountain range on Pluto. Remarkably, these rocks are probably composed mostly of water ice, which has a strength comparable to that of rocks at such low temperatures. A little to the south, you will see a deep basin surrounded by massive layered ridges of ice and rock. It is assumed that this may be the vent of an ancient cryovolcano, and the surrounding rocks may be its numerous frozen emissions. Their chemical composition is very interesting for science, because knowing it, you can study the peculiarities of Pluto's internal structure. The eastern part of the tomb region is colored darker. In addition, its surface is covered with many craters, meaning that the area is much older than the satellite plateau. As we move eastward along the equator, our eyes see a chain of dark spots hundreds of kilometers wide. These objects are called spots and are named after dark gods of various cultures. For example, one of them is called Balruk. Together, they form a giant structure called a nebula, which covers the celestial body along the equator. The spots are separated by high mountain ranges, and their surface is riddled with deep cracks hundreds of kilometers long. Cthulhu's macula, Pluto's largest dark spot, is nearly 3,000 kilometers long and stretches west of the tomb region. Its surface reflects no more than 30% of the light falling on it, which contrasts sharply with the bright pale plains of the neighboring satellite. So far, there is no reliable information about what the spot is. Their dark color is thought to be due to their high talon content, which, together with the relatively high content of impact craters, indicates their antiquity. The surface of Macula Cthulhu is also known to be heterogeneous. Thus, its western part has a hilly terrain. The central part is a flat plain, and the eastern part is covered with mountains and craters. Leaving Cthulhu's dark spot behind, we head north. It is the Lowell region, a vast valley surrounding Pluto's north pole. Surprisingly, this particular point is currently the most illuminated area on the surface of the celestial body. The fact is that the inclination of Pluto's own axis of rotation with respect to the plane of its orbit is very large. Therefore, in its movement, the celestial body turned to the Sun at the North Pole. This is thought to be why Pluto's atmospheric density has tripled in the last 30 years, even as its distance from the star has increased. The Sun's rays are likely to vaporize the nitrogen ice accumulated at the poles and replenish the dwarf planet's gas envelope. Pluto has several peculiarities in its orbital motion compared to the planets of the solar system. In addition to the significant inclination of its orbit to the ecliptic plane, the planetoid itself constantly makes cyclic oscillations near a certain point. This is due to the presence of a large satellite that exerts a gravitational influence on the dwarf planet. It is called Charon and has a mass of 1.52 x 10, 21 kilograms, which is more than 11% of Pluto's own mass. As a result, both celestial bodies rotate around a single center of mass between them. The objects are in mutual tidal entrapment and are constantly turned to face each other with the other side facing away from them. Unlike Pluto, the surface of this moon is much darker and has a lot of water ice, with only an occasional mixture of sour cream and nitrogen. In addition to Charon, there are several other satellites, but they are all much smaller and irregularly shaped. Discovered in 2005, Nicta and Kydra are tens of kilometers long, and later discovered Kerber and Styx do not exceed 16 kilometers in diameter. All of these celestial bodies are composed mostly of water ice, and are probably trapped in the Kuiper belt by Pluto's gravity. Unfortunately, much of Charon was not in the field of view of the cameras of the New Horizons probe. However, many interesting landforms can be found on the visible surface of the celestial body. For example, there is a large area south of the equator called the Valley of Volcanoes. Its area is not known exactly, but it is at least 400,000 square kilometers, which is comparable to the size of an average European country. This is where Charon's highest peak, Mount Kubrick, is located. According to some estimates, it has a diameter of about 40 kilometers and a height of 4,000 meters. In addition, the mountain is surrounded by a wide circular moat up to 2 kilometers deep. Some have speculated that Mount Kubrick may be a cryovolcano. In this case, it is very likely that the surrounding area collapsed under its own weight due to the emptying of an underground reservoir. To the north lies the vast country of Oz, with many craters on its surface. It is separated from the volcanic valley by a system of giant ledges and breaches with a total height of about a kilometer. The largest of these is the Serenity Gap, which is 200 kilometers long and 50 kilometers wide. It can be up to 7 kilometers deep. In addition, its bottom is quite difficult to study due to the thick shadows created by the steep slopes. Farther north, right at the pole, darkens the Giant of Mordor. Its diameter is 475 kilometers, and its origin is still controversial. The current hypothesis is that the nitrogen and methane that escaped from Pluto's atmosphere were captured by Charon's gravity and deposited at its poles. Under the influence of ultraviolet light, they became talons and gradually concentrated in the ice of the celestial body. This assumption needs to be tested, which is the goal of future missions. Charon is still a mystery to us in many ways, as it has only just begun to be explored. Although the Pluto-Charon system is undoubtedly one of the most interesting structures in the solar system, it is still poorly understood. Unfortunately, New Horizons hardware has long since left its environment, and the celestial bodies themselves are rapidly moving away from us, robbing them of their secrets. The probe is currently more than 50 astronomical units away from Earth and continues to send us rare but very important information. Around 2030, all of its systems completely fail, and the device is left all alone in the cold depths of space. Comets are small solar system objects that orbit the Sun and can be seen as bright dots with a long tail. They are interesting for several reasons. Since ancient times, people have observed comets in the sky. Only once every 10 years can we see a comet from Earth with the naked eye. Its impressive tail flickers across the sky for days or weeks. In ancient times, comets were considered a curse or a sign of past troubles. A comet gets its name from the Greek word for long-haired, because the ancient Greeks thought comets looked like stars with shiny hair. Comets have tails only when they get close to the Sun. When comets are far from the Sun, they are exceptionally dark, cold, and icy objects. The remaining body is called the nucleus. It makes up 90% of a comet's mass. The nucleus is made up of different kinds of ice, dirt, and dust. Ice, on the other hand, contains both frozen water and impurities of various gases such as ammonia, carbon, methane, etc., and in the middle is a small rocky nucleus. As it approaches the Sun, the ice begins to heat up and vaporize, releasing gases and dust particles that form a cloud or atmosphere around the comet called a coma. As the comet continues to approach the Sun, the pressure of sunlight from the Sun begins to blow dust particles and other debris out of the comet. This process creates a dust tail. If the tail is bright enough, we can see it from the ground as sunlight reflects off the dust particles. Comets usually also have a second tail. This is called an ion or gas. An ion is formed when atomic ice is heated and turns directly into gases, bypassing the liquid phase. The process is called sublimation. The residual gas is visible due to the glow caused by solar radiation. As comets begin to move away from the Sun, their activity decreases and their tails and coma disappear. They return to a simple ice nucleus. And as comets orbit back toward the Sun, the comet's head and tail begin to form again. Comets come in a wide variety of sizes. The nucleus size of the smallest comets can be as large as 16 kilometers. The largest nucleus turned out to be about 40 kilometers in diameter. The tail of dust and ions can be huge. The ion tail of comet Hyakutake stretched a distance of about 580 million kilometers. There are many versions of the origin of comets, but the most common is that comets formed from the remnants of matter during the formation of the solar system. Some scientists believe that comets brought water and organic matter to Earth, which became the source of life. Meteor showers can be observed when the Earth's orbit crosses the trail of debris left by a comet. It is not known how many comets exist because most have never been observed, but a group of comets called the Kuiper Belt is located 480 million kilometers from Pluto. The solar system is surrounded by another such cluster called the Oort cloud. it can simultaneously contain more than 1 trillion comets moving in different directions. Since 2010, astronomers have detected about 4,000 comets in our solar system. Seeing a comet is in many ways a miracle that many people dream of seeing at least once in their lifetime. But in very rare cases, comets can cause problems on Earth. Most scientists believe that about 65 million years ago, Earth may have been struck by a very large asteroid or comet. The resulting changes on Earth led to the extinction of the dinosaurs. Very large asteroids and very large comets can cause significant damage when they reach Earth. However, scientists believe that large impacts, like the one that killed the dinosaurs, occur every few 100 million years. Comets can change direction for a number of reasons. If they passed close enough to the planet's gravitational pull could slightly alter the comet's trajectory. Jupiter, the largest planet, is the most suitable planet to change the path of a comet. Telescopes and spacecraft have taken pictures of at least one comet, Shoemaker-Levy 9, when it crashed into Jupiter's atmosphere. In addition, sometimes comets heading toward the Sun hit the Sun directly.